Hello everyone. So I'm doing this video not in the classroom because the projector was not working. Anyway, we're gonna cover the very last topic today for the course, which is going to be a different approach to clustering than k-means, which is based on something called Gaussian mixture models. And to fit those models, we're going to learn about expectation maximization. And then finally, we will compare this to k-means on a new problem. All right, so let's start at the beginning. So for the the place to start is a multivariate Gaussian distribution. So this is something you guys have seen before, but let's just review it. So the idea is that when you have data that looks like this, where you can see you have sort of a cluster of samples with some sort of oval shape, then a good model for this is Gaussian. So here we have features in 2 dimensions, so we'd want to use a 2-dimensional Gaussian. That's also known as a multivariate Gaussian. And the PDF of a multivariate Gaussian, let's call the data x, so the PDF probability of x. We write it as this with this script n. Here, x is the variable, q is the mean vector, and mu is the mean vector, and q is the covariance matrix. And when you look at how that's formed, it's an exponentiated quadratic form. We have x minus mu transpose x minus mu here, and then in the middle we have the inverse covariance matrix. And we need that the entire PDF integrates to 1, so we have to apply this scale factor, and then that gives us a valid PDF. Scale factor is the determinant of 2 pi times q raised to the power minus 1/2. Okay, so when you're looking at data like this, and you wonder, okay, how do I make sense of what we see? So we have like the center of this cluster of points. Well, we know that the center here is going to correspond to the mean of the distribution. Well, what about how the data is stretched? In this case, it looks like there's sort of an oval shape here. And yes, it turns out that for a multivariate Gaussian, if you plot, here we're plotting the PDF in 2 dimensions, and we have these level sets here. These level sets are, in fact, or sometimes we call them contours, these are ellipsoidal. So there's level sets that are ellipses like this. Now, if you want to know, how to parameterize those ellipses, well, for the ellipse, we have a principal axis. We have 2 principal axes, and it turns out that those principal axes are determined by the eigenvectors of the covariance matrix Q. So here we've done an eigenvalue decomposition of Q, orthogonal matrix V, diagonal matrix lambda V transpose. So when you look at the columns of V, they tell you the directions of the principal axes, and remember that if Q is a covariance matrix, we know that the columns of V are orthogonal, and that is what we need here. Okay, then what about how much one is stretched relative to the other? That is coded in the eigenvalues. So it turns out that the principal axes are stretched by the kth principal axis is stretched by lambda k to the minus 1/2 power. So lambda k is the kth eigenvalue. Okay, so when we use these multivariate Gaussian models, we have a pretty convenient expression. We can sort of understand what's going on from the ellipses and the ellipsoidal cos contours, and it's a good approach if we have data that looks like this. Now, sometimes we instead have data that looks like this. So here, if we just consider these points, this looks like a good candidate for a Gaussian model and multivariate Gaussian, and you can see that I'm going to have a particular mean, and I'm going to have particular, I have ellipses with particular eigenvalues or principal axes, and we can connect those to the covariance matrix associated with this Gaussian. But then we have another Gaussian over here, and the data could come from either of those two Gaussians. So when we have that possibility of more than one Gaussian, call that a Gaussian mixture model, a GMM. So this is a weighted sum of k different Gaussian PDFs in general. In this plot, capital K is 2. And then the way the PDF looks is just a sum over the different components. Each one is a multivariate Gaussian with its own mean and covariance. So here, these would be the two means, and you could see by how the different ellipses are stretched, they would have different covariance matrices. And then we have these weight parameters. These are the weights that tell us essentially how likely it is to draw, or how probable it is to draw one of these Gaussians, k equals 1 versus k equals 2. And so for these parameters, in order for this to be a valid PDF, we need that those guys are non-negative and that they sum to 1. Okay, so overall, the kth PDF has mean mu k, covariance qk, and the weight gamma k controls the probability of the kth component. Okay, and this actually gives us a very natural way to do clustering. So the first step is you would take your data set, xi, where I goes from 1 to n, and you would fit the Gaussian mixture model parameters. So you'd figure out which gamma k, mu k, and qk are the best fit to this. So we're going to explore that in a few slides. We're going to use something that's an approximation of maximum likelihood, because it turns out maximum likelihood is a little too difficult for this problem. Okay, now let's assume that we've figured out what our parameters are, so we know our probabilistic model. We have this. The next step, to cluster a test sample X, we would just determine which of the Gaussian mixture model components is more probable. So for example, if X was over here, then you could evaluate how probable is it to get that sample from this distribution versus that sample from this distribution. And you can actually compute those two probability values, and then you can just choose the one that's higher, and that will tell you which cluster it comes from. Okay, so that's basically how we can use a GMM to cluster. But to understand a few details, we want to rewrite the GMM in what we call a hierarchical form. So the way we can think about this is, imagine that you wanted to create a data set, simulate a data set from a given Gaussian mixture model. So someone tells you the gamma k's, mu k's, q k's, and then you want to generate dots like these that came from that, that distribution. So the way you could do that is you could do this in two steps. In the first step, you draw a component index that's going to be an integer from 1 to k, and then, given the index you draw x according to the Gaussian PDF. So over here in this picture, I would first draw number 1 or 2. I would want to think about them randomly. So we, to do that, so we have a discrete random variable in this case with two possibilities, 1 or 2. And we could think of a PMF that would have gamma 1 is the probability of drawing k equals 1, and gamma 2 is the probability of drawing k equals 2. And so I would randomly draw a random variable. We're going to call it kappa, so the component index. I would draw kappa based on that PMF, and let's say that the value I draw is going to be called k. And then, now that I know which cluster it's coming from, let's say it came from this cluster, I know that this is a multivariate Gaussian, so I can draw samples from that Gaussian distribution. Okay. So that's the second step. So we're using this fixed value of kappa. In particular, we're calling it kappa equals k. Okay, so we have the concept of the probability that kappa equals k. We know this is gamma k. And second, the probability that the probability of x, given that the cluster is k, or the component is k. This is just a Gaussian with mean mu k and covariance qk. Okay, so this is a different way of thinking about this, where we've introduced one additional random variable, kappa. So kappa is not necessarily visible here. The only random variable we have here is x. But what we're doing is we're thinking of sort of inserting a new random variable in the model. And here's another way to think about it. So by the law of total probability, this is here the joint PDF of x and kappa being k. So we can integrate out essentially the kappa random variable, and we know that gives us just the marginal probability px. But we also know that we can write this as a product of this conditional px given kappa times the probability of kappa. And when you think about it this way, now we can relate it to what we've done above, where you know that probability x given kappa is going to be, or in particular given kappa equals k, is this. And then the probability that kappa equals k is gamma k. Okay, so this is known as a hidden variable. Kappa is what's called a hidden variable. And it doesn't explicitly appear in the original definition of px, but we can certainly use it as a way of thinking about how x is generated. And this is going to be the key for us when we do clustering. We're going to think of kappa as telling us the index of the two components. And if I get a sample here, I'm going to evaluate the probability that kappa equals 1 given the sample x, or I can also evaluate the probability that kappa equals 2 given x, and I can choose the higher of the two probabilities. That tells me the more probable value of kappa. Okay. All right, so let's just describe that last idea with some equations. So what we're doing is we are starting with P of x, the Gaussian mixture model. We're writing it this way. We're saying we have a sum over k, where we sum the probability of kappa equals k times the probability of x given k. And as we saw in the last slide, the probability of kappa equals k, are there's these numbers gamma k, and the probability x given kappa equals k is a multivariate Gaussian with mean mu k, covariance qk. Okay, so to do the clustering, we're going to use map estimation. In other words, finding the most probable component index kappa associated with x. So we have to evaluate this thing, probability that kappa equals k given x. We don't directly know the value of this, but using Bayes' rule, we can figure it out. Remember, Bayes' rule allows us to reverse the order of the conditioning. Basically allows us to write it as probability x given kappa equals k times probability kappa equals k divided by probability of x. And now you can see we can use this here, we use this here, and we use this whole thing here, and we have a new expression for this, which involves quantities that we know. Okay, so assuming that we have trained our model, we know all these different parameters. If we have a new test sample x, or even a training sample x, we can plug that in here, and we can evaluate the probability of kappa equals k for that given x. And that's going to be a number between 0 and 1, and that's what we call a soft assignment. Very similar to our soft probabilities in classification. So once we know those soft assignments, if you want to turn them into hard assignments, you just find the index K of the largest soft assignment. Okay, and that would give you the hard assignments. Okay, so that's how we'll do our clustering. So let's just summarize everything up till now. This Gaussian mixture model-based clustering of dataset X of I is done in 2 steps. First, we're going to fit the GMM parameters. We'll call those parameters theta. As we know, they include all the weights, gamma k, all the means, mu k, all the covariances, qk. We'll fit those parameters to the data. We haven't talked about how we're doing that yet. That will be the next topic. Assuming we've done that, then for every data sample I and every component k, compute the soft probability, the probability that kappa I equals k given xi. Okay, so here kappa I corresponds to xi. And we know from the expression on the previous page that equals this, so we can just plug in all this stuff, compute this value between 0 and 1. And actually we do that, for all I, for all k. And then for all I, for all data samples, we can compute the hard assignments. We look at the different values as the components range from 1 to capital K. We find the maximizing soft value. Whatever index k maximizes that, we're going to call that kappa hat of xi. Okay, so that's a summary of what we've done. Now, next topic, to fit the Gaussian mixture model parameters, ideally, we would like to use maximum likelihood. As we know, maximum likelihood goes like this. We want to maximize the probability of x given theta. Theta are our parameters. We know that that's the same thing as maximizing the log probability or even minimizing the negative log probability or likelihood here. And furthermore, in this problem, the log likelihood, again, we're going to assume, like always, that these xi are generated independently. Then the log likelihood gives us sum over the samples times the log of, in this case, probability of x given theta. Now, unfortunately, this is not something that we can simplify further. We have the log of a sum of Gaussians. If we didn't have a sum, you just have the log of a Gaussian, we know that that simplifies nicely into a quadratic plus another scaling term. But when you have a sum of Gaussians, there's really no way to simplify it. So this is actually a difficult non-convex optimization problem. It's very prone to falling into, if you try to optimize it, very prone to local minima or local maxima. So it's not something we can do directly. So instead of using maximum likelihood, we're going to use an approximation to maximum likelihood called the expectation maximization algorithm, the EM algorithm. Okay, so that's the next topic of discussion. Okay, so to start from the beginning, the EM algorithm is an iterative approximation to ML estimation. You can use this anytime you have a maximum likelihood estimation problem. If your maximum likelihood problem is convex, you don't really, your log likelihood is concave, actually. If your negative log likelihood is convex, you don't need to do this. But if it's non-convex and difficult to solve, it's one of the most commonly used approaches to get around those issues. So what's nice about it is it's guaranteed to converge to a local maximum of the likelihood function. So that's, of course, not, that's part of what we want, but we want more than that. We would like it to converge to a global maximum. That's, again, very difficult. In this case, with the EM algorithm, you need a good initialization to avoid those bad local maxima. But in many applications, there are ways to get those good initializations. So we'll talk about that in addition later for this Gaussian mixture model fitting problem. But let's just focus on the generic EM algorithm applied generally to maximizing the likelihood. Okay, so the main idea behind EM is you have to choose some things called hidden variables. These are variables that essentially make the problem tractable. There's many choices of these variables in general, but often there's maybe one choice that kind of sticks out as a good choice. And the approach alternates between two steps, a first step called the E step and a second step called the M step. So it looks a little bit complicated, so let's try to break this down. So in the E step, what you're doing is you're computing a function. In the M step, you're maximizing that function over the unknown parameters theta. But notice there's another thing here called theta t. Theta t is your guess or your estimate of those parameters at iteration t. So as you can see, what's happening in the M step is you do this maximization over theta, this free variable, using your guess from the previous step, and that gives you your guess on theta for the next step. And then when you come to this E step, or iteration, when you come to this E step, here we see the guess being used, and here we have the free variable. So we don't want to confuse theta t and theta. They're very different. So this is going to be a function of theta that is that uses your guess of theta at iteration t. Okay, let's look more closely about what is this function q. So here we have a conditional expectation. So this is the thing we are averaging, this log, and notice that this is a joint. This is not px given z, this is px and z. So we're looking at the average value of this, but when we're computing that average, we're using a distribution. We're looking at averaging over z for fixed value of our data x and for a fixed guess of our parameters theta t. So in fact, we can write this q like this. So here we're writing it more explicitly. This is our conditional expectation. So this is the argument of the expectation that appears here. And then this determines the PDF we're using for our averaging. So here's our variable z that we're averaging over. So this is an integral over all the possibilities of z. Here's our conditional distribution, probability of z given our data x and our old parameters. And as we said, this is the thing we're averaging over. So the way we think about this probability of z is we think about it as a belief. It's a belief on the hidden parameters. In particular, we're expressing it not as just a single vector z, but here like you could say a posterior distribution. It tells us what are the most likely values, or what for every possible z, how probable is that z given the data we have observed and given our current estimate of theta. So let me just give you one example. This is sort of the simplest case. Let's say that you were absolutely confident that z is something called z hat at iteration t. It's just your guess of z at iteration t. So that would mean if you're completely confident that z is this, you would use a Dirac delta distribution, a spike located that turns on when z is z hat t. So that could be one simple choice in here. And if you put this thing in here and you carry out this integral due to the sifting property, your Q function will be exactly this, just the log of the joint probability P evaluated at X and this Z hat T. Now, in general, you don't believe that you're not absolutely confident that Z is Z hat T. there's many z's that you think could exist, many values of z that you think could exist at this point. So that's why you use this whole distribution across different possibilities of z. So when you think about this Q function, you're basically averaging this quantity over all the probable values of z. Okay, so it's averaging this joint log distribution over all probable values of z. Okay, and so let's go a little deeper to understand why, what we said earlier, that this is it's connected to maximum likelihood estimation. So far it's not really clear how it's connected to maximum likelihood estimation. Okay, so let's make that connection clear. So imagine that we have some, again, this is going to be a belief on z. We're going to call it p hat on z. It just functions as some belief about random variable z. Later on, we will connect it back to this particular form here, but for now, it's not really important. In fact, this can be any PDF. You can construct p hat any way you like, as long as it's a valid PDF. Okay, so let's start with our log likelihood. Okay, so if this is our log likelihood, notice that I can stick this inside this integral, because in fact, since this log PDF has nothing to do with z, we could pull this to the front, and what remains then is just the integral of over p hat, which we know as a valid PDF integrates out to 1. Okay, so this is why we can write it this way. It might look weird. We have a nice simple thing here. Now we're writing it in a much more complex way. Okay, well, let's stay tuned. So we're going to write it in an even more complex way. We're going to expand this probability here, probability of x, into this. Okay, so notice that to understand why this is equal to the probability of x, let's notice that those cancel out. And finally, if you go through the math, the joint probability of z and x divided by the probability of z given x can be simplified down to probability of x. Okay, so this is just a more complicated way of writing p of x. And finally, we get to the point of why we're doing all this. Remember that if you have the log of a over b, that gives you the log of a minus the log of b. And here we have another thing over here. So we have log of this minus log of this plus log of this. So that's what we've done to get these three terms here. We can then split that into three different integrals. And let's take a close look at what these are. So the very first integral, this is exactly this thing that we saw similar to our Q function. We're averaging over our belief function of the log of the joint probability. The second term, which is capturing this is something that if you have seen any information theory, you would recognize that this is the entropy of the p hat distribution. Okay, it's sort of a measure of how much randomness there is in p hat. And then finally, this last term here is something known as the KL divergence and the Kullback-Leibler divergence. And this quantity is known to be non-negative, no matter what. No matter how you choose p hat of z, this is always going to be non-negative. Okay, and so the reason why we're doing this is we have now a new expression for this log likelihood equaling this first thing plus the entropy plus this last term, which is non-negative. And if you think about that, if you want to come up with a lower bound on this, because this is 0 or positive, the first two terms are a lower bound on this, because we need to add a positive number or non-negative number to get back up to this. So this would be a lower bound. So that is what gives us this equation. The log likelihood is lower bounded by this sum of the first two terms. We're going to give this a special name. This is going to be this L function, lower bound on log likelihood. And you can see it's a function really of two things. It's a function of our p-hat distribution, which shows up in these two terms here, and it's a function of our theta variables, which are used here. Of course, it's also a function of our data x, but what's most important is how it depends right now on p-hat and theta. And basically, the way that the EM algorithm works is it iterates the following two steps. We have this lower bound. First, we tighten the lower bound by choosing p-hat. Second, we maximize the lower bound through choice of theta. So let me illustrate this with this picture on the right. So this triangle shape function, this is like our log likelihood. This is something we want to maximize. So we want to find this theta, since this gives us the peak. But maybe we could say this is a difficult function to maximize because, as you can see, it's not differentiable. So maybe we can do this iteratively by computing the lower bound, optimizing the lower bound, computing a new lower bound, optimizing that, and so on. So what we do is we start with some guess of theta. Let's say that our initial guess of theta is here. Then what we're going to do is we're going to come up with a lower bound that is tight at theta. So we're going to construct, in this case, this quadratic function that you can see at lower bounds. Lower bounds are log likelihood, but it actually is a tight lower bound. So this is going to be our L p-hat at theta. I'll call this maybe theta 1. And let me try to... So that first theta is theta 1 over here. Okay, and so that's the E step, is we figure out this lower bound. Next step, in the M step, is we maximize the lower bound by choosing theta. So as you can see, just with this lower bound alone, if I want to maximize this, that would just be the top of the parabola here. So that would be my new theta, which we can call theta 2. And now I would repeat. I would come up with a new lower bound that would be tight at this point. It would be another parabola, maybe something like this. And then I would optimize that. So I would find the peak of that. That would occur at this value, theta 3. And then that would give me a new point. I would come up with a new upper bound, and so on. And you would keep making upper bounds, and you would climb and climb and climb. And eventually, asymptotically, you would reach this theta. Okay, so essentially, like in this simple example, this has allowed us to get around the non-differentiability of the likelihood function. Earlier in the semester, we talked about maximizing or minimizing the likelihood, the log likelihood, maximizing log likelihood by setting the gradient equal to 0. But as you can see, that wouldn't work here because we have a non-differentiable log likelihood. So that method doesn't work. However, this EM algorithm would work. It would eventually converge to the maximum likelihood estimate of theta. Okay, so that hopefully gives you a little bit of a flavor of what's going on, we can fill in a few more details. So the first comment is that this procedure that we're using here, where you iterate tightening and maximizing lower bound, this is actually a more general procedure known as majorization minimization. And majorization minimization has a lot of applications, and EM, you could just say, is one special case of it. It's just one application of MM. Okay, so in this special case, how exactly do we do the bound tightening? How do we do the E step? Okay, so remember that okay, so this is our log likelihood, and we're going to have, as you can see, expectation over p hat of the log of the joint. So here, expectation of p hat of the log of the joint, plus we have our entropy term, and this is an equality, so I'm also including the KL term, which we know is non-negative. Okay, so let's see. So I basically just rewrote this expression from the previous slide. So how would you come up with the bound tightening? How do you do the E step? We need to choose p hat so that the lower bound is as tight as possible. Well, in this case, because it's possible to make this KL term exactly equal to 0, if you could do that, then your lower bound would coincide exactly with your likelihood, and it would be perfectly tight. So how do we do that? Well, notice that if I can make what's inside the log here equal to 1, then log of 1 is 0, and then that 0 would turn this whole integral into 0. So in other words, all we have to do for the E step is to set our p hat function equal to this. And so this explains why the EM algorithm uses this particular function in place of p hat. Okay. Now what about the M step? So at iteration t, we want to maximize this for the given value of p hat. Well, when you look at this, we want to maximize this over theta. This entropy term has nothing to do with theta, so we don't have to consider it when we maximize over theta. So we really just have to maximize this term over theta. But that's exactly what we said the EM algorithm is doing. It just maximizes this first term. Oh, sorry. The M step is maximizing this function q over theta. Okay, so that hopefully that explains everything. Just to review, we start with the likelihood. We expand it in a very particular way where this one term here is non-negative. That allows us to define a lower bound on the log likelihood. We then iterate this maximization or majorization minimization approach. We tighten the lower bound by choosing p hat, maximize the lower bound by choosing theta, and iterate. And when we plug in everything, we find that we should choose p hat as this quantity, we should choose theta as the maximizer of this. Okay, so that hopefully explains the EM algorithm in general. Next task for us is to apply the EM algorithm to Gaussian mixture model fitting. So we're going to start with the E step. So the first thing we have to do is choose our hidden variables. So the way we'd like to do this for a Gaussian mixture model fitting is that we're going to choose kappa I. Kappa I, if you remember, that's going to be the integer that tells us which component xi was generated from in that hierarchical model. Okay, so these are random variables. We're going to be estimating them iteratively. That's how we can think about kappa I is the which component is associated with xi. And so previously when we were deriving it, we were using z. So now this z matrix is just going to be this kappa vector. So this is the q function written with the kappa vector in place of z, but otherwise identical expression from before. Okay, so we need to simplify this. So let's first take a look at this probability of x and kappa. So this is where we can see the benefit of choosing this particular form for the hidden information. So under the assumption that the xi's are independently generated, if you tell me, so basically this joint distribution separates into a product over your data samples I of these marginal distributions. Each one has the data sample xi and kappa I, which is the component membership for xi. So this is going to lead to a lot of simplifications because remember that the log of a product is going to be the sum of the log of this stuff. And that sum over I, we can move that out to the front over here. And then what that means is that what remains here is basically the log of this term, which only depends on a single one of the kappas, particularly the ith kappa. So when we do this integration over all the kappas, essentially all but kappa I fall away. Because let's say if we're looking at a term kappa j where j is not equal to I, this does not depend on kappa j, so you could imagine taking that out. And then you have, here you have probability of kappa I and all those other kappa j's, but you're just going to integrate out the kappa j component because you know that this integrates to 1 for all the different kappa j's. It's only the kappa I term that's more difficult because kappa I appears in 2 places. Okay, so that's the justification of why this k vector can be replaced with the ki scalar. And then this becomes a scalar distribution, and this, as we said before, came from this. Okay, so now this is much simpler. We have a single integral, single variable of integration, but actually when you think about this, we don't want to integrate because these kappas are discrete random variables. So rather than expressing this using an integral, let me write it as a sum over all the possibilities of what kappa I can be. So this, to expand it, this would be like kappa going from 1 to capital K. And now this PDF, we should express this as a PMF. So this is the probability that kappa K, the kappa I equals K. And similarly over here, actually this should also be expressed as a probability of this discrete value of kappa. And furthermore, we can write this joint probability as a conditional times a marginal. So probability xi given kappa I equals k times the probability that kappa I equals k. And these are things that we know. This is just a multivariate Gaussian. This is just our gamma k. And now again, I want to emphasize the difference between the theta t and the theta. So theta t are numbers, or quantities that we've already computed, whereas these are free variables that we want to use when we do the optimization in the M step. Okay, so so again, for these guys, the probability of xi given kappa I equals k, that takes this form. So here, theta, if you remember, is going to be mu k and qk. So we're just explicitly expanding this into the unknown parameters. Over here, the probability that kappa I equals k, that's just the value gamma k. which is one of the elements of theta. On the other hand, this probability kappa I equals xi, we can rewrite this with Bayes' rule, exactly like we did on the other page. And now we're writing things in terms of specific quantities that we have estimated. Okay, so these things with the superscript t are different than these things without the superscript t. These guys are variables, whereas these are quantities that we actually computed. So we also know our data, so basically we can evaluate all this and boil this down to a single number, and we can compute that number for all classes or components k and for all data samples I. Okay, so finally, this gives us our Q function. The Q function, let's take a look at exactly what it looks like. So down here, again, these are just going to be numbers, just values we've computed. So we can do this log of this product as the log of the first plus the log of the second. So here we have the log of the second here and the log of the first here. And you can see in both cases we have double sum over I and k scaled by those computed quantities. Okay, so this is the value, this is the function that in the m step we want to maximize over theta. In other words, we want to maximize over this gamma k, mu k, and qk. So let's talk about how we do the maximization over gamma k. So one thing that's important to remember is that these weights have to sum to 1. It turns out that they also need to, if you remember, they are also non-negative. But it turns out that we don't have to explicitly enforce the non-negativity. It's okay, this will happen naturally, but we do have to explicitly enforce the summing to 1 constraint. Okay, and finally, when we maximize over gamma k, you can see there's no gamma k's over here, so we can forget about that. We just need to maximize this thing over gamma k. Okay, so this is the objective, and this is how we enforce the constraint. So back in Unit 6, we talked about constrained optimization, talked about adding new optimization variables. In this case, it's this Lagrange multiplier lambda. And we write lambda times the thing we want to force to 0. So if the gamma k is summed to 1, then this thing goes to 0. Okay, so what we do is we want to jointly optimize this over all the gamma k's as well as over lambda. So as we often do, we're going to take the gradient of our cost with respect to gamma k, set that equal to 0. So when you look at this, the gradient of this, we're looking at a particular value of k here. So only one of the terms in this sum will matter, and it's the term where kappa prime equals kappa. Sorry, k prime equals k. And when we take this derivative, we get 1 over gamma k. So here's the 1 over gamma k. And then we still have a sum over I that hasn't changed. So we have a sum over I of these variables here. And we also need to take the gradient of this with respect to gamma k. Something similar happens. Okay, so first of all, this term goes away. Over here, there's only one term in the sum that matters. It's the term when kappa prime equals kappa. And at that point, the sum reduces to gamma k. And when we take the gradient of gamma k with respect to gamma k, we just get 1. So we get lambda, or minus lambda. Okay, so we need to force this equal to 0. If you rearrange it, you can see by multiplying both sides by gamma k, we need that this equals 0. And, well, if this equals 0, then if I sum both sides over k, then the sum of this over k should also be 0. So that's where we get this. The reason we're doing that is we can make some simplifications because we know that the sum of the gamma k's over k needs to be equal to 1. So this goes away. And in fact, this too, for each I, the sum of the gamma kt's over k must sum to 1. So that goes to 1. So we still have the sum over I, value 1, and then minus lambda. So this, because I goes from 1 to n, this first sum reduces to n, the second one is minus lambda, and so now 0 equals this, we know that lambda equals n, and so this basically tells us the value of the Lagrange multiplier, lambda, which is the other variable we needed to optimize over. Okay, so now that we know lambda, we can focus on optimizing over our gamma k's. So to do this, what we do is we return to this equation here. We rearrange it to extract our gamma k, so we bring this term over to the other side. We divide both sides by lambda. That gives us this down here. We plug in lambda equals n. It gives us this. And now this is a quantity that we know. We know all these numbers. We sum them. We divide by n. This is going to be the value, the optimal value of lambda k for the next iteration. So this is what we use as our guess for the next iteration. Okay, so that's the first thing. We just figured out how to optimize over the gamma k's. Next, let's figure out how to optimize over the mu k's. Okay, so for the mu k's, we can forget about this term. Just focus on this term over here. So that's what we get here. And I've written this sum over k prime so we don't confuse it with k. And to do this, to take this gradient over mu k, by linearity, we can move that in front of this natural log. And in fact, we can expand the natural log. Log of this Gaussian is going to give us this quadratic term plus a constant. This term, this is from the scaling factor. This is not a function of mu k, so it's not important to know what the value is. And finally, we take the gradient of this with respect to mu k. That's something we've seen before in some of our earlier units. When it has this quadratic form like this, we end up getting this for the gradient. And now we want to set this to 0. We don't yet know qk, so let's try to get around that. So notice this is a sum over I, so that means we can actually move qk inverse, that matrix multiply, to the outside, as long as we basically it's sort of like moving this sum over I on the other side of qk. And so this is what we have on the other side of qk. And as you can see, we need that the 0 vector equals this, and assuming that qk inverse exists, that would mean that this term actually, this vector needs to be 0 for this to go to 0. We're going to assume in general, so if this covariance matrix is full rank, and Q inverse is full rank, which means the only way to get a vector that multiplies this to 0 is for that vector itself to be 0. Okay, so finally, we know that this guy here equals the 0 vector, and then we can just rearrange to extract mu k, and we get this expression for mu k. So this is the optimal mu k, and we're going to use this as our guess for the next iteration, so we'll call this mu k t plus 1. So I'm not going to go through the derivation for optimizing qk, but it's pretty similar, and when you go through that, you finally get qk t plus 1. So we've actually made it all the way through the algorithm, so let's just summarize it. So the first thing we have to do is we have to initialize our parameters, or initialize our guess of gamma k, mu k, and qk for all the different clusters or components k. And then once we have that initialization, we can just repeat this loop over these 4 steps for iterations t equals 0, 1, 2, and so on. So what we derived is that knowing the values of these parameters, you can compute these numbers. These are sort of, you could think of them as soft assignments. The vector for each fixed I, the vector over k is a PMF of the class membership or the component membership of xi. So we compute that. Once we know those variables, we plug them into the sum. This gives us our gamma k for the next iteration. Then we can use those variables again over here to get our mu k for the next iteration. And it turns out that the qk update looks like this. This is qk for the next iteration. And we just repeat this until convergence. One last question is, how do you initialize these? Very common approach is to use k-means, k-means plus plus. In particular, what k-means will give you is hard cluster assignments. And so what you do is you set this first term, gamma k0, to the fraction of samples that k-means assigned to k. And finally, you can set the mean and covariance quantities, initialize them at the mean and covariance of the samples that k-means assigned to k. Okay, so we can basically use k-means plus plus to get these values, and then we run the EM iteration to fit the GMM parameters. Now, just one other note is that in high dimensions, this covariance matrix here has, if the dimension is d, this has d squared parameters. So that can be expensive to compute, and you in fact might not even have enough samples here to make this Q full rank. So what people often do is they just approximate Q as diagonal, which is sort of like in these pictures here. Sorry, it's all the way back here. It's equivalent to setting the principal axes parallel to the coordinate axes. That's what happens when you have a diagonal. You can't stretch your ellipses in a diagonal way like this. You have to have ellipses that are principal axes are parallel to the coordinate axes. All right, so that summarizes how we apply EM to GMM fitting. And finally, let's go through an example on a small data set. So these show the iterations. These circles and ellipses, they show a contour of the fit of the Gaussian. So in this case, we're going to have k equals 2 components. So this little k will range from 1 to 2. So we're going to have, for each little k, we're going to have a mean and a covariance. We're going to initialize the covariances to be identity, which means we get circular contours. You can see one of the means is over here and the other mean is over here. And these soft assignments, these are these gamma ki's, they show for each sample I, whether that's assigned to this component or this one. We're going to use colors of the dots. So when you see a blue dot, that means that it's much more, that the soft assignment indicates that blue dot corresponds more to this. A red dot corresponds more to this. And a purple dot would mean that it's somewhere in between. So we have like kind of a range of colors that range from red to pure blue that show our soft assignments. And also, I took this from a textbook that used L for iteration, not T. Okay, so this is how we initialize. So here's, we're going to just initialize our centers here, our covariances. We set identity, and this is just our data points. So the very first thing we do is we use those initializations and our data to compute all our soft assignments. And so you can see for each one of these data samples, the color shows our soft assignment, and not surprisingly, the ones that are close to this mean, they're more red. The ones that are close to this mean are more blue, and the ones that are sort of in the middle are purplish. Okay. The next thing is, once we have those soft assignments, we can update all our parameters, and what that's going to do is that's going to change the mean of our ellipses as well as the covariance, which tells us, how the ellipses are stretched. And based on those, based on the new ellipses, we then compute new cluster assignments by plugging the new parameters in here, new cluster assignments. And we keep redoing that. So new ellipse gives us new colors gives us new ellipses, and this is iteration 1, iteration 2, iteration 5, iteration 20. You can see how gradually these ellipses move over and become better linked to these two clusters here. Okay, so just an illustration of the EM algorithm. All right, so this EM algorithm is actually not so different from k-means. Let's talk about some of the similarities and differences. So both of them are iterative algorithms, but EM computes soft assignments, these probabilities, while k-means computes hard assignments, so just integers. EM estimates the covariances, whereas k-means implicitly uses scaled identities where epsilon is a very small number. And the result of that is, if you remember with k-means, the decision boundaries we had were linear. In this case, they'd look like this. But with EM, because you can have different matrices, different covariance matrices, you actually get curved decision boundaries. So it's a little bit more sophisticated. K-means piecewise linear. Okay, another thing is that EM actually estimates the weights that tell you, how many data samples correspond to one Gaussian versus another, whereas k-means implicitly uses 1 over capital K, as the weights for all of the different components. So EM is, you could say, more general, maybe more precise, but it's more computationally expensive than k-means. Also, both of them can get stuck in local minima. Both benefit from good initializations, and both are implemented in scikit-learn. So in scikit-learn, there's this Gaussian mixture, and you can see you just specify how many components and so on, how many iterations, how you would like to initialize it, and then you do gmm.fit, and then you can do gmm.predict to get the hard assignments. Okay, so let's look at an interesting application of this to color quantization. So we're going to start with this image here. This is a standard, what they call true color image. This image has red, green, and blue panes. So you could say that this is like a sum of a red brightness image, a green brightness image, and a blue brightness image. Each of those 3 sub-images have 8 bits per pixel. So for each pixel, there's 2 to the power 8, or 256 color possibilities. Now, if you think about the 3 of them together, they have 24 bits per pixel of color. And if you think about, basically 2 to the 24th is 16 million different color possibilities for these true color images. So each pixel is one of 16 or almost 17 million different colors. Now, in an image of a certain size, especially when the size is less than 16 million, you're not going to have every one of these color possibilities manifest. So for this image, it turned out that there was about 97,000 different colors that were represented in this image. So our goal is to try to compress the image by reducing the color palette down to 16 possibilities, down from almost 17 million. So in other words, rather than 24 bits per pixel, I want to reproduce my image using only 4 bits per pixel, because 2 to the 4 is 16. So the question is, what are the 16 best colors that can minimize the RSS, the sum squared error, compared to the true unquantized image? So we can treat this as a clustering problem. Basically, our signal space, we can think of just working in a space where xi is going to be a 3-dimensional vector, like red, green, blue. And we have many, many samples of xi in this image. And we want to figure out 16 different centroids within this space, 16 numbers that are going to be, in some sense closest to the original data. So we want to learn these centroids. Now we're not going to use all the samples from here. We're going to use 1,000 random pixels from there just to speed things up. The total number of pixels in this image is 273,000. So that would take maybe too long to run the EM algorithm. So we're just going to use 1,000 samples. That's enough. And we're going to try to figure out these 16 centroids, which will give us our 16 best colors. And basically, we're going to try this with 2 methods: expectation maximization based GMM and k-means plus. So we know how to do both of those. We can do both of them with scikit-learn pretty easily. So let's take a look at what we get. So this is showing the quantized image with our Gaussian mixture model. So the first thing you can notice when you look at the sky is that there's like 1, 2, 3, 4 different colors which are used for the sky. Here you had very smooth gradients, thousands of colors were used for the sky. Here it's just 4. And so you do have these kind of weird boundaries. Let's take a look at some of the other things, like there is an island over here with a bridge connecting to it. And let's notice how well we can make out those details. What else? We can also look at the horizon. We can see here, there's just a couple colors assigned to the horizon. So this is what we get with GMM. Now let's look at what we get with k-means. So when we look at, let's say this island and the bridge, you can see that k-means is not doing as well of a job of representing that island. Trying to see what else we could gather from this comparison. Yeah, I think that's probably, also here you can see there's kind of, maybe you could say it's kind of weird to get this sky color here, whereas this is doing a better job at the horizon. But basically, we can see that this EM algorithm is doing a better job preserving the fine details because it's a more sophisticated approach. It's more general, also more computationally expensive. Okay, so that concludes our treatment of GMMs and expectation maximization. Just a couple more slides left. One thing we haven't talked about at all is this model order selection problem, in that both k-means and EM-GMM require that the user specify how many components you would like to cluster. Now, you could say that that's a weakness because maybe in practice we don't know how many clusters we would expect. So there are other clustering methods that do learn that number automatically. These are just a few. We'll show you some examples on the next page. But that is one issue for k-means and EM-GMM. There are some approaches that have been proposed to try to address that in those algorithms, sort of like extra steps you can take. Another question you could use is, what features should we use to do that clustering? Should we use the original raw features, or should we do a nonlinear transformation of our features similar to what we did with regression and classification? Should we use, for example, like a kernel method? And the answer is yes, you can do that, and it's known as spectral clustering. So here's just sort of a example that's from scikit-learn, some of its documentation, that shows 1, 2, 3, 4, 5, 6 different data sets, and then it shows about 9 different approaches, and just with these toy examples, just looks at how they work on clustering. So here on the left we have mini batch k-means, which is just a sort of an approach of k-means that works on mini batches, and then here on the right we have Gaussian mixture. So those are the approaches we've covered, but you can see there's a lot of other approaches here. Spectral clustering is like that kernel-based k-means and so on. And you can see how they work to varying degrees of success on these different data sets. So like for these data sets, you can see k-means is basically failing to pull out the structure. Same thing with Gaussian mixture. They're just not equipped to do that. But some of these other techniques, they do very well in terms of clustering those shapes. We can also look at something like this. So here, I would say Gaussian mixture maybe is doing a better job than k-means. K-means is sort of having trouble with this middle cluster, and but you can also see other approaches are doing quite well, just like Gaussian mixture. And yeah, here Gaussian mixture is doing great on this. K-means is failing, but we have some other examples. Other algorithms do well as well too, but other ones fail. This is sort of an easy one. I think everyone does well on that. And then this is a really hard one. Just kind of, it's interesting to see what these different algorithms do. But some of them, can recognize that these are all from the same class, same component. So that's all that I have for this unit, and this is the last unit of the semester. So we'll have just one quiz on this, but then other than that, you just have the final project to work on. I hope the final project is going well for you, and can let me know if you have any questions. Otherwise, I hope you enjoyed the class, and please let me know on the SEIs if there's things that you liked or think could be improved with this class. I'm always trying to make adjustments and make the experience better for the next semester. So thanks again for all your hard work. I hope you enjoyed the class, and I'll see you around.